Welcome to The Explainer. Today we're jumping headfirst into RAID 6 on Linux. We're going to show you exactly how to build a storage array that can survive not just one, but two hard drive failures at the same time. Seriously, if you're in charge of any kind of critical data, this is for you.
So, here's what we've got on tap. We'll kick things off with the what and why of RAID 6, and then we're going to get our hands dirty and build an array from scratch. Then, and this is the fun part, we're going to break it on purpose, just to see it survive. After that, we'll walk through the rebuild and finish up with some absolutely crucial pro tips.
All right, first things first. What is RAID 6 anyway? Well, to put it simply, when it comes to protecting your data from a hardware meltdown, it's pretty much the ultimate safety net.
Okay, this question right here. This is the entire reason RAID 6 even exists. You know, with something more common like RAID 5, if a second disk dies while the first one is rebuilding, poof, your data is just gone. It's a total loss. RAID 6 is specifically designed to make sure that absolute nightmare scenario doesn't happen.
Now, the secret sauce here is something called dual parity. Think of it like a really simple math problem. If I tell you 2 plus x equals 5, you can instantly figure out that x has to be 3, right? Well, RAID uses a similar idea to create redundant data. And by having two separate sets of this parity information, the system can solve for two missing pieces of data. That's how it survives two drives failing. It's pretty clever.
Let's just quickly break down what this really means for you. You need at least 4 disks, and that's because you need space for your actual data, plus those 2 disks worth of parity. So yeah, you're basically trading the capacity of 2 whole drives for some serious peace of mind. And this becomes absolutely critical when you're dealing with big arrays, say over 10 terabytes, because rebuilding a single failed drive can take days, and you're vulnerable that whole time. Okay, enough theory. Let's actually build one of these things. We're going to be using MDADM, which is pretty much the standard tool in Linux for software RAID. Let's just walk through it, step by step. So, it really boils down to 4 main steps. First, we've got to prep our physical disks and partition them. Then, we use one single command to actually create the array. After that, we do a quick check to make sure it's healthy, and finally, we format it and mount it so we can start throwing files on it.
This command right here is the magic wand. We're telling mdadm to -create a new device. We're just calling it /dev/md0. Then the -L6 part says, hey, make this a RAID 6 array. The -N4 tells it we're using 4 disks, and then we just list out the partitions we want to use. That's it.
And here is how we know it worked. We just check this little status file called mdstat. And this output, UUUU, that is exactly what you want to see. Each U stands for up, which means all 4 of our disks are online, active, and happy in their new array. Okay, now for the really fun part. We're going to take our shiny new array, and we are going to break it. On purpose. This is where we put RAID 6 to the ultimate test and see just how tough it really is. So to fake a disk failure, we use that same mdadm command, but this time with a -F flag to mark a disk as faulty. Now, when we check mdstat again, look at that. The status changed to U_UU. That little underscore, that's our failed disk. The array is now in what's called a degraded state, but, and this is the key part, it's still 100% functional.
And now, let's really push our luck. Let's fail a second disk. We run the command again, and now the status shows UUU. 2 underscores, 2 offline disks. This is the exact moment that a RAID 5 array would have completely collapsed. For RAID 6, this is where it shines.
So this is it, right? This is the scenario we've been talking about. We've got 2 dead drives in a 4-drive array. You'd think our data is toast. So what happened to all the files we put on there?
And the answer is nope, not at all. The data is still 100% there. We can read from it, we can write to it, no problem. Now don't get me wrong, the array is in a super critical state and needs attention, like yesterday. But our data is safe. That is the power of dual parity in action.
Awesome. So our array survived the disaster drill. But we can't just leave it like this. Right now, it has 0 redundancy left. If a third disk fails, we are done for. So let's go through how to replace those failed disks and get this array back to a healthy, fully protected state. The recovery is actually pretty straightforward. It's a 3-step process. First, we have to officially tell the array to remove the faulty disks. Then, we add our new, healthy replacement disks. And finally, we just get to sit back and watch as the array automatically rebuilds and heals itself.
So, once you have new physical disks in the machine and you've partitioned them, this single command is all it takes. You use the IA flag for add, and that tells MDADEM, hey, add these new disks to the array. As soon as you hit enter, it automatically kicks off the whole rebuild process.
And you can literally watch this happen in real time by checking MDStat. The array rebuilds one disk at a time. So you'll see the status go from UOO to something like UUO as that first new disk gets synced up. And once that's finished, it'll start on the second one, until finally it's back to that beautiful, healthy UUU state.
Okay, so now you know the mechanics, how to build it, how to break it, and how to fix it. Let's talk about the stuff that separates a weekend project from a truly professional, reliable setup.
Think of this slide as your cheat sheet. You've got -create to build the array, -F to fail a disk for testing, -R to remove a bad one, and -A to add a replacement. And of course, your best friend, cat/proc/mdstat to check on how everything's doing. These are really the core commands you'll be using day to day.
Seriously, do not skip these steps. This is absolutely essential stuff. Use enterprise drives. They're built to run 24/7, unlike desktop drives. Always save your config file, otherwise your array might not even show up after a reboot. And you have to be proactive. Use tools like smartctl to monitor disk health, and schedule regular scrubs to find and fix silent errors before a drive actually fails.
And finally, remember, it's all about using the right tool for the job. RAID 6 is this amazing sweet spot of safety and capacity, especially for critical data. Now, if you need the absolute fastest write performance you can get, RAID 10 might be better, but you'll lose half of your total storage space. And RAID 5, honestly, with how big hard drives are today, it's just gotten too risky for anything important. Let's end with this because it's so important. RAID is not a backup. It protects you from hardware failure, but it won't save you from accidentally deleting a file or ransomware or data corruption. It's an amazing last line of defense for your hardware, but that's what it is, a line of defense. So, with that in mind, here's a question for you. What's the very first health check you're going to automate for your array?